All objects emit electromagnetic radiation. The electromagnetic radiation's frequency depends on the object's temperature. Cold objects emit waves with low frequencies, while hot objects emit waves with higher frequency. Do humans also emit electromagnetic radiation? A black body is an idealized body that is able to absorb all electromagnetic radiation that falls on it. A black body can also emit thermal radiation depending on its temperature. The radiation emitted forms a continuous spectrum and is unaffected by the nature of the black body's surface. Thus, an object emitting electromagnetic radiation which is determined by its temperature is known as a black body radiator. As the temperature of an object rises, the object acts as a black body radiator and emits thermal radiation of all wavelengths. This figure shows a graph of radiation intensity against wavelengths. Usually, every curved graph of the black body spectrum is narrower on its left, which is an area with short wavelengths and high frequencies. With increasing temperatures, the wavelengths approaching maximum radiation intensity will also get shorter. Ideas that sparked the quantum physics theory. Light is an electromagnetic wave that is produced from the vibration of an electric charge. In a hot object, electrons vibrate rapidly and randomly in any direction and produce light. According to classical theory, electrons vibrating at the same frequency should have the same energy content. The vibration frequency of an electron also has no limits. Thus, the light energy produced by the vibration of electrons can reach unlimited high values. However, experimental results involving black body radiation are inconsistent with classical physics theory. Based on the graph of radiation intensity against wavelength for the black body radiation, the light intensity on the left side of the peak does not continue to increase with the increase of wave frequency as predicted by classical theory. This controversy in the concept of light energy has sparked the theory of quantum physics. The electromagnetic spectrum may be a continuous spectrum or a line spectrum. The dispersion of white light by a prism produces a continuous spectrum consisting of 7 visible colors. The line spectrum produced by an excited atom is a series of colored lines with unique wavelengths and frequencies. Therefore, the line spectrum can be used to identify the presence of an element. Table shows the frequency and quantum energy values of the line spectrum produced by a mercury vapor lamp. Quantum of energy. Quantum of energy is discrete energy packet and not a continuous energy. E is equal to hf, where E is photon energy, h is Planck constant, and f is the frequency of light waves. Example question. Compare the energy of a 400 nanometers and a 750 nanometers light photons. First, we have to identify the problem, then identify the information given. Next, identify the formula to be used, and last, solve the problem numerically. Wave-particle duality. Electrons are said to have wave-particle duality because they exhibit the properties of both particles and waves. Light also possesses both wave and particle properties. Electromagnetic radiation, such as light, is said to have wave properties because it exhibits the phenomena of diffraction and interference. Objects like marbles are said to have particle properties because they possess momentum and kinetic energy and can collide with each other. In 1924, Louis de Broglie, a quantum physicist, had to put forward a hypothesis stating all particles can exhibit wave characteristics. The greater the momentum of the particle, the shorter the wavelength. Since the value of momentum of particle can be determined by P equals to mv, the following formula can also be obtained. Since the value of each is very small, particles of large masses will have de Broglie wavelengths which are too short to be detected. Therefore, the wave characteristics cannot be observed. In 1927, the presence of wave properties of electrons was confirmed through electron diffraction experiments. This is the diffraction pattern of electron through a thin layer of graphite. This pattern resembles the red light diffraction patterns through an aperture as shown in here. This confirmed de Broglie's hypothesis. Electrons are said to have wave-particle duality because they exhibit the properties of both particles and waves. Light also possesses both wave and particle properties. The E equals to hf equation can also be replaced by E equals to hc over lambda. When a metal surface is illuminated by a beam of light at a certain frequency, electrons can be emitted from the metal. This phenomenon is known as photoelectric effect. When a light-sensitive metal surface, cathode, is illuminated with a certain light beam, electrons will be emitted from the metal surface. These electrons are called photoelectrons. The emitted photoelectrons are attracted to the anode, which has positive potential. The movement of photoelectrons from the cathode to anode produces a current inside the circuit. The milliammeter shows the value of current. There are 4 characteristics of photoelectric effect. Number 1. The higher the frequency of the photon of light, the higher the kinetic energy of the photoelectrons emitted from the metal surface. Second, the minimum frequency of light needed for a metal to emit electrons is known as the threshold frequency, FO, for what that matter. Next, the kinetic energy of photoelectrons does not depend on the intensity of light. An increase in the light intensity does not produce photoelectrons with a higher kinetic energy. And lastly, photoelectrons are emitted instantaneously when a metal surface is illuminated by light. The emission of electrons from a metal surface by photoelectric effect is instantaneous. The emission